I'm here with Tim Maudlin. Tim, thanks so much for joining me.
Glad to be here.
Tim, I'd like to start off talking about someone who's an intellectual hero of mine, and I think is an intellectual hero of many physicists, which is Richard Feynman, one of the
Mhm.
most influential physicists of our time, and considered um, one of the most sort of influential figures in quantum mechanics as well. He actually has a famous quote, which is "Philosophy of science is as useful to scientists as ornithology is to birds," and I believe that was him. What do you make of a statement like that?
Well, I'll just give you my usual response to that, which is a simple fact. Namely, ornithology would be of great use to birds if they were smart enough to understand, right? I mean, it's a very silly quote, right? In a way, of course, birds would benefit from understanding birds uh, and how birds work. They would understand their predators. They would understand their prey. They would be more efficient as birds. They're just not bright enough to do ornithology. Okay. So the quote makes no sense from a logical point of view. Philosophers of science are interested in the structure of science and how it works. Not all the work in philosophy of science is really great. Not all the work done by philosophers is really great. You get the right people, you get people who thought deeply about things, and they're going to be relevant to doing science. Um, you so it's a strange kind of, I mean, Feynman had a strange kind of disdain for philosophers, which I take it as a function of the philosophers he happened to run into and happened to talk to. And, for certain ones, I understand that. But to make a blanket statement like that is just kind of silly.
Yeah. I mean, it's interesting because Feynman was really philosophical in other areas. In many ways, his approach to physics was very different from what you would find in the standard textbook. His way of communicating physics was often very philosophical. Do you think he actually intended that statement to be sort of in disdain to philosophers of science?
Yeah. Look, it was obviously in disdain to philosophers in general. I mean, that was his intention.
Yeah.
And I don't, again, I would have to know who he was interacting with and what kind of conversations he was having to understand why he would say that. I can say it had a bad effect. I mean, I once heard Murray Gell-Mann kept actually tried to out Feynman and literally got a note from his doctor saying, "Do not, he's not allowed to talk to philosophers because it's bad for his blood pressure," or something like that. It's just a pose. I mean, Feynman. The great thing about Feynman was he really did want to understand things. He really had a deep desire not to merely calculate, and there are wonderful stories about this, but to deeply comprehend what's going on. He was very frustrated with quantum mechanics, as he said. He said he didn't understand it. After all his work with it, he said he didn't really understand it. And that's great. And of course, the people in philosophy really want to understand the people who are doing it well. And so there's no natural tension at all between science as Feynman wanted to do it and philosophy of science as good philosophers of science do it. Uh,
Mm.
I like to say that the greatest philosopher of physics in the first half of the 20th century was Albert Einstein, and in the second half was John Bell. I believe that's true. They had philosophical ability and they understood philosophical issues and they had talent at what's key to philosophy, which is very clear comprehension, stating the problem in a very precise way, understanding, what a certain solution would require of you and so on. These are the sorts of things that are developed by a philosophical training, and they just had it. Einstein, of course, read a lot of philosophy when he was young. He talked about reading Hume and so on. So I just don't think, you would have to go back. If it's really true Feynman said that, you'd have to understand when he said it, what kind of philosophers he was talking to, what the issues were. There, there are philosophers who, if you talk about almost anything, what you'll get will be pretty useless. Unfortunately, there are physicists of exactly the same sort. I mean, this is humanity. So I think the general that statement was not helpful. And I would hope if you sat down and talked to him for a little while, he would, just say, "Oh, I was being facetious or something.
Mhm. Yeah, you mentioned some names there that were very influential in quantum mechanics, and I would love to get to them and talk about their contributions. But maybe zooming out a little bit before we do, just setting the picture a little bit about, what is the philosophy of science, and in particular the philosophy of physics. How would we define that and distinguish it from physics itself? Because those two individuals and several others who've been very influential in physics itself have also been very philosophically minded. And if you look further back in history, many of the most influential scientists have really been philosophers. So, how would we define philosophy of science and distinguish it from the actual practice of science?
Well, the second part I wouldn't do. Um, and, I often say, if you ask me what I do, I say I do foundations of physics. And if someone says, well, why aren't you in a physics department? I say, yeah, there are people in physics departments who do it too. And there are people in math departments who do it too, do the very same thing. There isn't a distinction between a certain branch or part of philosophy of physics and physics. It is just physics being pursued at a certain fundamental level and with certain fundamental questions in mind. Now, philosophy of science goes a bit broader. I mean, I often say you can kind of take the broad house of philosophy of science and divide it into three parts. So for any X, there is the philosophy of X, right? There's philosophy of mind, there's philosophy of sport, there's philosophy of chemistry. That is, take any topic and ask certain fundamental questions about it. Philosophy of art, and you have philosophy of it, right? So there's always philosophy of X. And so there's science as the object of study of philosophical method, raising certain philosophical questions. That's one part. There's a second part, which is take certain traditional philosophical problems, like what is space? What is time? I mean, these are things that philosophers worried about forever. And say, well, science has some things to say about that. You should take into account the science, the results of science in pursuing those questions. So that's input from science into philosophy. And then there's another part, which is asking foundational questions about the science that typically the scientists don't ask or don't spend a lot of time on, where you're now saying, look, it's not that the physicists or the biologists or whatever have worked all this stuff out and we just have to go ask them. There are questions that they need to address that actually we're gonna go into because they're kind of leaving them aside. And this happens all the time in philosophy of biology and in evolutionary theory. There's a thing called the units of selection controversy about whether you should think of evolution as proceeding by selecting genes or selecting phenotypes. I mean, I could go into a million examples where the question is just a scientific question, but it tends to lie on the more conceptual side or be connected into other broader issues like causation and explanation and so on, that the philosophers have tended to think about more deeply and rigorously than most scientists have. And so, at that point, there just is no distinction between doing the science and doing the philosophy of it. You're doing the same thing. Um, you bring a slightly different toolkit to the same questions.
Yeah, then where do you think the sort of sometimes you find a little bit of disdain or a little bit of resistance within physics departments, for example, towards philosophy? Where would that come from if there is such a close relationship with doing philosophy of science and doing physics in practice?
Right. I mean, this is clearly a historical thing that happened. As you say, Newton was very philosophical. I mean, Newton, you go back and read the Principia, and as I mentioned, there's this question, what is the nature of space and time? And Newton writes a
Mhm.
scholia exactly on that question and gets into debates with Leibniz, who is also both a philosopher and a mathematician and a physicist and they have a dispute about the nature of space and time. Um, this is just you can't make it to say, of course, what Newton was doing, what he called what he was doing was natural philosophy, right? It was mathematical principles of natural philosophy. So what we call physics was just regarded as a part of philosophy. Um, that got messed up by quantum mechanics. If you ask me, why this hostility? The answer is quantum mechanics. And the deeper thing about that is that there are some very basic and simple questions one can ask about quantum mechanics that, because of the influence of Bohr and because of the influence of Copenhagen, I mean, there's a whole story here, a physicist is not able to answer, right? Questions, a freshman will put up their hand and ask that are perfectly good physics questions, and they don't have an answer for it. But they're more, you might say, philosophical sounding question. Right? What really is an electron? Does an electron really go through two slits, on its way to the screen? That's a physics question, right? That's not a philosophical question. That's just a physics question. What, do electrons really orbit atoms? Like the pictures seem to suggest. What is a wave function? I mean, these are physics questions, but physicists are not trained to address them. It's not part of a physics curriculum to address them. It's part of a physics training to ignore them. I mean, this is where you get this mantra of shut up and calculate. It's like, look, I'll give you some math and I'll explain to you how to use the math to make some predictions. And after that, shut up, right? Don't ask me what it means, right? Don't ask me what is the picture of the physical world that we're getting out of this. That's somehow supposed to be a bad question. Well, it's not a bad question. It's a great question. And it's not a philosophical question per se. It's a physics question. But physicists are not trained to address that. And so I think that's where, if you ask me, I think that's where the hostility comes from, is embarrassment. It's just embarrassment. It's like, yeah, I can't answer, sorry, freshman, I can't answer your question. You don't want to just stand up in front of the class and say, that's a good question. I can't answer it, right? So you say, oh, that's philosophy. Go and talk to somebody else, blah, blah, blah. I mean, I have firsthand accounts of exactly this, of students interested in physics, go to talk to their physics professors and ask questions, foundational questions about physics. And after 5 minutes, the physicists get mad and say, oh, go to the philosophy department. I don't deal with that. But they're not asking philosophical questions. They're asking physics questions. And the professors just don't have any answers. So they get mad. Okay, that's human nature.
Yeah, that's well, your account very much resonates. Also, firsthand experience with that. Learning, I guess, the first quantum mechanics course I took in undergraduate. When we got to the collapse of the wave function and the description, I think it was
Yeah.
positioned as a postulate. So we just had to accept it as a
Mhm.
postulate. I won't say who was the person teaching that course, but they're well known. And I find this very strange, not just I mean, I was pre-wired to believe that quantum mechanics was going to be strange, but what I found more strange was just the approach to suddenly taking on sort of a different attitude towards what physics is at this point of the the collapse
Right.
postulate, and not being willing to sort of explain or dig into what's going on here in the way you would do in any other area of physics. So I'm
Right.
definitely keen to dig into this and what's causing this. Maybe just to sort of set the scene a little bit. I don't want to shy away from difficult topics in this conversation. I also do want to assume that there'll be people listening to this who maybe have never taken a course in quantum mechanics or studied it, and so I think it's probably worthwhile briefly laying out some of the basic elements before digging into it. So could
That's
you
fine.
set the
Can I
scene?
can I just make a quick comment? Just again, for people who don't know this, you might be
Sure.
surprised. Start out by saying you were expecting quantum mechanics to be strange, which is of course fine. I mean, it's not the way you think about the world. But that's equally true of relativity. Relativity presents a theory of space and time, which is not the way you think about it. But there's a huge contrast between the two. That is, these sorts of foundation, the more you work with relativity, the more you understand it. And there's no mystery about it. You just don't have this lingering sense of, I don't get this, right? The more you work with it, the more you do get it. And you can answer straightforward questions, physical questions quickly and cleanly and say, oh, this is how it goes. And I can do this to some extent, and I know relativists who are just great. You ask them anything, oh, there's a star, this is happening, and what's going to happen, and they'll give you an answer that you understand. It's just in quantum mechanics. It's not the strangeness, right? Strangeness isn't the issue. We can deal with strangeness as long as we have a clear account to grasp. And the problem in quantum mechanics is you don't have one. There's certainly no standard, clear account of what the theory is even postulating.
Yeah. I mean, I would actually love to get your views on whether that's true historically for other paradigms that have shifted. And I know you're sort of very close to the history on many of these things. I take, for example, the introduction of imaginary numbers into mathematics. Um, they appear in maths and they appear in many, many places in physics. And now they would be accepted by anyone who uses them. Engineers using them in sort of electrical engineering would use them and not think a second thought. But at the time of introduction, this is a pretty weird idea. Would that sort of introduction of this new theory, this new way of doing things, have been as philosophically inflammatory as quantum mechanics, well, has been and is currently, or is this something completely different?
Well, let me again just make a quick comment about the issue of imaginary numbers, because that splits into two parts. One is pure mathematics, right? Forget physics. I'm just a mathematician. I'm doing number theory. I understand the integers. I understand the real number line. I understand how to multiply and divide all of these numbers and get more numbers. And then somebody says, well, what if we, as it were, introduce or postulate, whatever you want to call it, a new kind of number that squares to -1, which no real number will, right? So if you only have the real number, you say, well, no number does that. And you say, fine, I'm going to introduce a new number that just has this property. It squares to -1. And now I'm going to explain to you how to manipulate that, how we can now make complex numbers that have a real and imaginary part, how to add them, how to multiply them. I'm going to give you all those tools. No mathematician is going to kick too much about that as long as you've nailed down exactly how you do the operations, the mathematical operations with them. All right. You've got a well-defined formal system. The real question was, okay, but if I'm doing physics, right? If I'm doing physics and I'm trying to use these numbers to represent the physical world, what does this imaginary number mean physically, right? What would it mean to say, you might say, what would it mean to say, I did an experiment and got the result, the number I? Now, there's a very interesting thing you can say about that. But the point is, there's the math by itself. And then there's a second question, which is the connection between the mathematics and the physical world. And people may think, well, it's a little harder to see what imaginary numbers have to do. It turns out to be very easy to answer that question. That's why if you're clear about it, depending on the application, the engineers are going to be fine because they can explain to you what the eye is doing. And from this point of view, I'll just say one more word. If that was your worry, if your worry was, I do a measurement and I get the answer I, what could that mean? You could raise that for negative numbers just as well, right? You say, well, what do you mean? What do you mean -2? I mean, I understand what it is to say I have 2 sheep. And I even understand what it is to say I have 0 sheep. It means I have no sheep. What would it mean to say I have -2 sheep, right? So if you get too caught up in that, you ought to say, why are you kicking all of a sudden at the imaginary numbers? You should have kicked already at the negative numbers. But the way we use negative numbers to do physics is so easy to understand. You just make a Cartesian coordinate system and, you lay out a grid and you've got these coordinates that go from positive to negative infinity. And these coordinates indicate points on the grid. Okay, it's not hard to understand the use of the negative numbers. And it's not at all hard to understand in certain circumstances the use of imaginary numbers. And in fact, there's an interesting story about trying to translate geometrical problems into algebraic terms and then solve them algebraically and then translate the solution back. And sometimes you would do that and you'd get imaginary numbers but they understood what that meant. It meant that you made an assumption about the solution that wasn't true, and the solutions are lying somewhere else on the plane. I mean, they came to understand how all that fits together. So the imaginary number one is kind of a different thing because it's not by itself a physical postulate at all. It's just a new piece of mathematical machinery that turns out to be very useful in doing certain kinds of physics.
Yeah. So so there's been this sort of transition from or I guess in that case, there's a level of comfort that comes with imaginary numbers, with negative numbers, because people understand that that as an object is not necessarily pointing to something that exists physically in the real world. It's machinery, it's useful. We understand it
Right.
represents things, but it is not the physical object itself. In
Right.
quantum mechanics, things get much more contested. There's the wave function. Who
Yes.
knows what that means? Let's dig into quantum mechanics then. Would you mind setting the scene just very briefly? What are the basic elements of quantum mechanics and leading us up, I guess, from maybe some of the experiments to the wave function, and then we can start, really talking about the wave function and what that means.
Right. So, I mean, a standard thing that's done, and I guess I'll start here. If I had much more time, I would do this probably in a different way. But people often start with a two-slit experiment. Um, Feynman, to go back to Feynman in his lectures claims that the two-slit experiment contains all of the mysteries of quantum mechanics. That turns out not to be true because of work that Bell did, which was after Feynman wrote that. Um, but but the normal story is I have a device I call, say, an electron, a source of electrons, or an electron gun or a cathode ray tube. And when I turn it on, if I turn it at a very low level, I get dots little bright dots that appear on a screen or on a photographic film that people normally understood as, well, they're these particles, right? And they had an electric charge. You could accelerate them because they had an electric charge, and you could manipulate them with magnetic fields. So you have an electron gun, and the picture in your head is, okay, I've got these electrons. I'm shooting them out one at a time, much the way I would shoot bullets out of a gun. And then you say, all right, between this and the screen, I'm going to put a wall. And in that wall, I'm going to put two slits. So that you would say, well, for the electron to get through, it's going to hit the wall unless it happens to go through one of these two slits. And you turn this thing on, and again, most of the electrons are in fact hit the wall, but some of them get through and get to the screen, and they again produce these individual dots. But what you find is that the pattern of dots, if you run this for a while and you accumulate the data, the pattern of the dots isn't really what you would have expected on this bullet picture, right? Because on the bullet picture, this is the way Feynman would put it: close one of the slits and just shoot these things through. Okay, you get a pattern of the bullets coming through. Close the other one and shoot them through. You get another pattern. What should happen if both the slits are open? Well, you just superimpose those two patterns. You'll get the ones that went through this slit and the ones that went through that slit. And your prediction would be, having looked at what happens with each slit alone open, that what I'll get with both of them open is just literally the sum of those two patterns. And that's not at all what happens. What happens is all of a sudden you get these stripes. You get a little thin region where there are lots of the electrons hit, then a little thin region where none of them hit, then another region where a lot of them do, then none, then a lot. All right, so you get a pattern like that, and any physicist is going to look at that and say, well, I understand what this is. This is an interference pattern. This is the same thing that would happen if you had water waves coming at a wall with two gaps in it. Because when the water wave hits the wall, you get these two semicircular waves, one coming out of each of the gaps, and those waves propagate, and where they overlap, they just add up. And so a crest adding to a crest makes something really big, a trough adding to a trough makes something really low. And most importantly, a crest adding to a trough cancels out. So you get interference, you get positive and negative interference. And if you just look at, everybody I hope has seen a water table or has seen pictures of this kind of interference, then it's very easy to see because of the way these two waves interfere with each other, you're going to get these regions with lots of wave activity followed by regions of no wave activity because everything's canceling, and then a lot and then none. So that interference pattern is indicative of waves and of interference. And importantly, to get the interference, you need a wave that's going through each slit. You need both of them together to add up and interfere. So what the interference suggests is that something is going through both slits, and following a kind of wave dynamics and interference. On the other hand, what you see on the screen in any case are just these individual dots, these individual flashes, or these individual marks. That's what reminds you or puts you in mind of particles. And so, you get a little puzzled about that, and you say, well, what's going on here, right? Is the electron really a particle? But then why am I getting this interference? Is the electron really a wave? But then why am I getting these dots, right? And if you put it that way, it is, of course, a bit puzzling. Now, having said, and from this, as I say, Feynman gives what's actually a bad argument in his lectures. Having given this example, he then gives a bad argument to say, oh, you can't understand this in classical terms. You can't understand it using classical probability theory. That's just untrue. And you can work through that argument and see where he made a mistake. But it is puzzling, and you would rather like a clear physical account of what's really going on. As it turns out, there are very different ways of understanding this experiment. And according to some, there is indeed an electron particle that in every given run goes through either one slit or the other, just the way you thought about the bullets. And then you say, but what about this interference? And the answer is, well, because there's this other wave-like thing that's also there that's guiding the particle. So this is as John Bell said, he couldn't understand why they were so puzzled by all this and say, why not the obvious solution? They're asking wave or particle, why not the obvious solution, which is wave and particle, right? There's, the interference suggests a wave and the dots suggest a particle. Okay, there's a wave and a particle. But they didn't like that. Okay, so then they say, oh, it's a wavicle, or, Bohr then had this whole very complicated story going on. There's other approaches where there is no particle. There just isn't an electron as a particle that goes through one slit or the other. There's really a wave-like thing. It's not a puzzle that it goes through both slits. It's not a puzzle that it interferes. The puzzle is, why do I get these dots? And for that, they bring in collapse of the wave function, which is the thing we started with. What is this collapse of the wave function? That somehow they'll say words like this. Oh, the screen measures position. And so when the electron wave interacts with the screen, it's forced to come up with a position. It doesn't really have a position, right? Before it hits the screen. And when it hits the screen, somehow the screen tells this wave, now act like a particle, right? Show up somewhere. And that transition, that showing up, is the collapse of the wave function. And somehow you get this localized spotty behavior because of the collapse. That's, of course, a much more puzzling story already than the one with both a particle and a wave, right? Because you want to say, well, how do screens tell electrons they now have to show up somewhere, right? What's this? You would want the physics of that, right? It seems like a very odd thing to just postulate, for many reasons. It's not the kind of thing that as the normal story is told, should be the kind of story that shows up in physics. Does that help?
Yeah.
I mean,
Yeah, no, for sure. And I think, so you mentioned sort of several different, what are sometimes called interpretations of this wave function thing. I think the first one,
right.
I take it, would have been Bohmian mechanics, or the pilot wave theory.
Yes.
And then
the second one is what's called a spontaneous collapse theory.
Yeah, that's right.
Yeah.
Yeah,
And
that's right.
I'll just say a word because it helps to keep track of the players. There's a way of setting this up where essentially there's a fundamental problem that you have three assertions which you cannot jointly hold all three, right? Just as a matter of logic, they're mutually incompatible. If you give up one of them, you end up with this kind of pilot wave picture. If you give up another, you end up with this collapse picture. And if you don't want to give up either of them, your only option leads you to what's called the many worlds theory, where at the end of the day, you say, well, really, it wasn't that only one spot formed on the screen, but the screen split into an infinitude of copies, all with spots in different places, stuff like that. I mean, everybody's watched enough movies to have a sense of what that is. So that gives you a pretty good, the first thing you want to ask somebody when they're trying to explain the physics underlying this behavior is, do you have this first kind of picture where, yes, there is an electron, it's a particle, it's in addition to this wave-like thing? Or the second picture where, no, but you only have this wave-like thing and it collapses. Or this third picture where you say, you only have this wave thing and it doesn't collapse, right? Those are your three options. And then there are different ways to implement each of those three options.
Yeah, great. I think, I mean, it's a great description. I would love to actually get through all of them, and in particular, just asking ourselves, what could a selection criteria be for kind of choosing any one of them? I guess if we look at the sort of the predictive power of any of these, I take it that it's all the same, right? We have a sort of a wave description of something or other, whether that represents something real or it represents knowledge, whatever it represents. You pump it through some machinery, you follow the recipe as you mentioned in your book, and presto, at the end of it, you get a prediction of some sort. You can make a sort of probabilistic statement about where the dot appears on the screen. If that's the case, and sort of however you look at this thing, the predictive power is exactly the same, then by what criteria could one sort of make an assessment of these different interpretations? How could you ever know if one person was right or wrong in choosing one of these interpretations of the wave function?
Right. So I'm just going to give I have a standard complaint, which I'll give here. I don't like this word interpretation. It's very misleading. What we have here are three different types of theories. It's not that there's one theory and different interpretations of it. There are three, because, I mean, look at it. The first theory says there is an electron as a particle. It travels from the source to the screen, and it goes through exactly one of those two slits, sometimes the right one, sometimes the left. The second one says there is no such particle. There is nothing that travels a particular trajectory from the source to the screen. Those aren't two different interpretations. They're two different theories. They're just telling you completely incompatible physical stories. They're they do give largely, if you set them up right, because there are lots of details in telling these stories. If you set them up right, they do give largely the same predictions. They do not give exactly the same prediction. Okay, that's just false. So if you thought, oh, these are different interpretations because they all make the same predictions, they do not make the same predictions. Absolutely not. And then the next question that comes in your mind is, well, if they don't make the same predictions, then why don't you just go into a lab and check? And the answer to that is, now when you ask, how do the predictions differ? They differ in very subtle ways that are just hard to get your hands on experimentally. But there are people doing experiments now and have been doing experiments for decades checking this, especially for the collapse theory, the second one. There's an experiment going on right now in Gran Sasso, deep under the ground in Italy, that's looking for evidence of these collapses, which, if that showed up, would just rule out the other two theories. They haven't found it, okay, but this is the differences are very are very subtle, and there are some adjustable parameters that you can move around to slightly change the predictions. So the first thought, which is, gee, they all make the same predictions. The answer is no, they don't. That's just false. Okay, it's false from beginning to end. Um, the reason you don't decide between them experimentally is that we don't quite know how to do the experiments or make the observations in situations where the predictions are really different. But we're making progress on it. It requires experimental skill, and it requires cleverness to figure that out. So that's, I mean, that sort of reinforces. I mean, I really want to hammer down on that, because it reinforces that this is not mere philosophy, or merely putting a gloss on some base theory, base, I don't know, whatever that everybody agrees on. Not true. Clearly, these are different physical theories, right? They make different predictions. Well, apart from saying different things, they literally make different predictions. Now, that's so the first thing I talked about, the pilot wave theory, and the last one, the many worlds theory, they don't have this collapse of the wave function at a fundamental level. So you want to divide your approaches into collapse approaches and non-collapse approaches. Because both of those theories don't have collapse of the wave function, you can't identify as easily experimental or predictive differences between them. It's not to say that that's impossible. The many worlds theory is a much harder theory to discuss because it's just much less clear, the physical picture it's giving you, than the other two.
Yeah. Well, actually, I would love to discuss those two, because I don't know if you met David Deutsche.
Sure, yeah.
I mean, he's a big proponent of many worlds, or at least a flavor of it. And his belief is that, the existence of quantum computing, and in particular factorization of large prime numbers using quantum algorithms, is in a sense evidence for for many worlds view, because he asks the question,
Yeah, it's not.
where does the
No,
factorization
I mean, he said that forever, and
Yeah.
it's just not true. The first theory, the pilot wave theory, which does not have the collapse of the wave function, is not a many worlds theory. It does not say if you put a cat into a certain device at the end, there are 2 cats or 1,000,000 cats, or it doesn't say if you shoot an electron at a screen, at the end of the day, there are now 1,000,000, an infinite number of screens with different spots on. It just is not a many worlds theory. And it makes precisely the same predictions about quantum computers as his theory does. And the collapse theories make exactly the same predictions, because in the course of doing a quantum computation of the kind he's talking about, factoring large numbers using Shor's algorithm, these collapses probably wouldn't occur. They are kind of rare if you're dealing with a relatively small number of particles. So they also make exactly the same predictions. So of these 3 approaches, only one is many worlds. But with respect to explaining quantum computation, they're exactly the same. So this is a bunch of rhetoric that Deutsch uses. He's used it forever. It's not true. It's just rhetoric. It's just selling, right? He's selling something. And it's unfortunate, because he's suggesting that, gee, just the 2-slit experiment somehow proves there's many worlds. It absolutely does not. The pilot wave theory will explain all of those phenomena. The collapse theory will explain all of those phenomena without many worlds. So it's just untrue. Okay. I mean, I get frustrated, as you can tell, because, there's this rhetoric, there's like this language that gets repeated by the many worlds advocates, and some of it traces back to Deutsch, and it's just demonstrably incorrect. And it doesn't help a discussion. It doesn't help a rational, clear discussion of the options for people to be saying false things about the ones they don't like. Anyway.
I like hearing what people think about David Deutsch, because he is very inflammatory on a lot of these topics. He definitely, yeah, he definitely sort of states things very strongly. One interesting aspect though there, even in the pilot wave theory, you at least in that theory you state what you believe to be physical things out there in the real world. Um,
Mhm.
and in addition to their physical existence, they've got some sort of guiding, I guess, the pilot wave, sort of guiding
Yeah.
their evolution. It's still a linear theory, and there is still the question, would us as human individuals, for example, be described by some collection of these constituent sort of smaller, particles and their waves? Um, is there sort of scope or any thought behind a a marriage of the two theories, or is many worlds, in your view, completely off the table for some reason?
It's not, I don't consider it to be completely off the table. I think understanding that as a physical theory, um, and there are two different aspects to this. One has to do that people have talked a lot about, and they acknowledge they have a problem with, is understanding what talk about probability means in the many worlds context. And that's very easy to understand. If I flip a coin and I say, look, this is a biased coin. So there's a 25% chance it lands heads and a 75% chance it lands tails. First of all, if I say that about a coin, you'd say, huh, all right, well, how do I get empirical evidence whether what you just told me is true? Obviously, if I flip it once, it'll just either land heads or tails. That's not going to tell me anything. And you say, yeah, okay, right. Flip it 100 times, flip it 1,000 times, flip it 1,000,000 times. And if what I told you about the probability is true, then the observed frequency with which it comes heads and tails will be very close, right, to 25% heads and 75% tails or whatever. Not exact, you can do all the math and all the statistics. How far away from exactly 25% should you expect it to be? All of that is, at least it's very straightforward to connect up what you observe empirically to the claims about probability. And it's also not that hard to understand what the claims about probability really amount to once you get into the guts of the microphysics, depending on how you do it. In the case of the many worlds theory, you're going to say, if it's as it were a quantum coin, every single time you flip it, the same thing happens, namely the world splits, and now there's a heads world and a tails world. And if you flip it a second time, now there's a heads world, a head tails world, a tails heads world, and a tails tails world. And if you flip it again, there'll now be 8 worlds. And if you flip it again, and you'll notice in saying that the percentage doesn't matter, right? The 25%, 75% bit doesn't come into it, because no matter what that number is, as long as it's not 1 and 0, you'll get this branching structure of worlds where every single collection of outcomes occurs in one of these branches.
Yeah, but David would say there's some sort of measure across these different spaces of universes and some sense of proportionality across the branching, and we would find ourselves
Yeah,
in.
you can, sure, you can say that, but the point is you can't see that measure. That's not something you can go into. You can't go to an experimentalist and say, okay, go measure this measure that stretches over many different worlds. They have no access to it. They have no empirical access to it. None, zero. All you can see in the lab is the actual frequency you got at the end of the day. So you have to connect up somehow, talk about probability with talk about frequencies in order for this to be a physical theory with empirical content. And the many worlds people have a hell of a problem trying to make that connection, where the other theories don't. I mean, the collapse theory, it's straightforward. It fundamentally is an indeterministic theory. It says, all right, at the end of the day, you're going to get a single outcome. And here are the probabilities of these various different outcomes. Just as you'd say if you throw a die, just as you say if you spin on a roulette wheel or whatever. Here are the different possible outcomes. Exactly one will occur. Here are the probabilities. If you want to check the probabilities, repeat the experiment many times and look at the frequencies. Okay. The many worlds people can't say that because there isn't a unique outcome. You always get all outcomes. Now, Deutsch can say, oh, I can somehow say that if I square the wave function, I get a measure, and this measure is, as you just said, something that's spread over all these worlds. Okay, so what? I don't see it. How does that affect my life, right? How does that affect me as a physicist? How does a measure over all these branches, which I have zero access to, why should I care about it? Um, so it's more than just saying, oh, I can come up with something in my theory, that this particular measure would be a measure of. It has to be the right kind of thing and connect up to experimental outcomes in the right kind of way for this to be an empirical theory, a theory where you can say, here's my evidence for it. So you have that problem. You have a much, much, much deeper problem in any theory. Now I'm going to group together the collapse theory, the standard collapse theories, and the many worlds theory. The way those were originally developed, they both agreed that, as Einstein would put it, the wave function is complete. So I have a system. Part of what I do when I describe it mathematically is to assign it a wave function, which is what we've been talking about. And then you have this very straightforward question. Okay, give me the wave function of that system. Does that nail down all of its physical properties or not? Is it a complete description or not a complete description? This was what Einstein, Podolsky, and Rosen were worried about in 1935 when they wrote the EBR paper. The title of the paper is Quantum Mechanical Description of Reality Complete? Question mark. Their answer was no. The pilot wave theory immediately says no. It says, look, I've got two things here. I've got this whatever's described by the wave function. And in addition, I've got these particles that are just like particles. They're like regular old Democritean particles. They're moving around. They make up, how to take a collection of particles and make a table or a chair or a cat out of them, right? You just put them together like Legos in the right way and you get it to move right. There you go. The many worlds theory, and at least the original version of the collapse theories, just seem to only have this wave function. And then you have the problem, well, what is that? I don't see wave functions. I mean, the irony here is people call the pilot wave theory a hidden variables theory, but it's really, as Bell again pointed out, it's the wave function of the quantum state that's hidden. You can't see it directly. You can't do an experiment. If I just hand you an electron in a box and say, okay, do an experiment on that electron to figure out what its wave function is, the answer is you can't. It's not possible. There is no such experiment. It's the wave function that's hidden. And then the question is, okay, but what do you see? Now, on the pilot wave picture, the answer is you see the particle positions, right? What you're seeing, the cat is made of particles. And when you see this thing walking around, it's those particles. Deutsch, I don't know, the many worlds people don't have any clear answer to this question. This is the question what Bell introduced under the term local beables. What are the local beables of your theory? Meaning, according to your theory, what exists in a small region of space-time, right? There might be things that exist only globally. There might be things that don't exist in space and time at all in a normal sense. Bell said, you better have something that just exists in space-time. Why? Because that's the way the world is presented to us. It's presented to us as a bunch of localized objects in space-time, tables and chairs and cats and pointers and stars and planets that have shapes that move around. You need something in your physics that's that. And the many worlds people don't have it. They just don't. I mean, there was David Wallace that had a proposal for something along these lines, but it certainly has not been generally adopted. I don't think Deutsch believes that. I don't know what Deutsch believes in terms of, he just wants to talk about the wave function as if you can tell the whole story and make physical sense of it with just that and with it never collapsing. And I mean, you can't, or at least there's no obvious way to do it. So the other question I would say, when someone says, look, I have an account of quantum mechanics. So I said, the first question is, okay, are you a additional variables person, like a pilot wave person? Are you a collapse person? Are you a many worlds person? Second question, what are your local beables? What do you claim to exist in space and time? Maybe you have stuff that isn't, and the pilot wave picture does have something that isn't, namely the wave function. It's not a local beable. It's real. It exists. It's important, but it's not local, and it doesn't tell you whether the cat's alive or dead. At the end of the Schrodinger cat experiment, in that theory, if you want to know, did the cat survive? You say, tell me what happened to the particles.
Hmm.
Tell me what happened to the particles, and I'll tell you very quickly whether the cat survived. Don't give me the wave function. The wave function won't tell me. At the end of the experiment, the wave function will have a piece corresponding to a live cat and a whole bunch of pieces corresponding to different dead cats. And I can stare at that from now until forever, and I won't pick up out of that whether the cat lived or died. But if you just tell me what the particles did, I'll tell you immediately whether the cat lived or died, right? You don't even have to tell me anything about the wave function. So, if you first put a proposal in one of these three boxes, and then you ask whatever it is, what are the local beables? And if they come back and say, well, I don't have any local beables, you should be very puzzled. I'm not going to say it's impossible to understand how this theory could connect up to the everyday world, but it sure isn't going to be easy. It's much easier to do if you have some local beables. Bell wrote a wonderful paper called The Theory of Local Beables, and he was trying to make this point. And people don't read that. I mean, I don't have the sense people read Bell's theorem and that has something else, is addressed as something else. But he made a very deep, important point in that paper on the theory of local beables, and I don't think it gets as much attention as it should.
Yeah, it doesn't. And I don't think sort of the pilot wave theory is very widely accepted as all, at least it wasn't when I learned quantum mechanics, and I don't
Sure.
believe it is now. And I would love to get your sense as to why that is the case. If it is a theory that has like a very clear statement of what actually exists out there in the world, it produces all the same predictions that we know and love from the rest of quantum mechanics. Why is it then that this theory has not gained mainstream? Well, mainstream is a strong word. Why has it not gained traction
Yeah,
as in the way we would expect?
and that's a wonderful question. That's the I mean, there are two steps here. First is to understand what the theory does.
Hmm.
Once you understand what the theory does, this second question pops up immediately. But then why don't we know about this theory? I learned physics. Why wasn't I told about this
Hmm.
theory? Now that's exactly what Bell asked. Bell has this paper called On the Impossible Pilot Wave. And in it, he says, why isn't it taught in textbooks? Not as the only way, but as one way to understand what's going on. Why is it ignored? What he says, when there are no good objections to it besides rhetoric, like saying, oh, it's metaphysical, right? I mean, this is the kind of thing Bohr might say or Heisenberg might say. They use bad philosophical arguments to try and ignore the theory. Now, I can say, when I learned physics, I was certainly never taught the theory. And I guess there were two phases to why I might be told not to pay attention to the theory. One, very ironically, was the claim that, oh, we know the theory must be false because Bell proved you can't have hidden variables theories, right? Or von Neumann even earlier proved you can't have hidden variables theories. But ironically, people often say, oh, Bell ruled that out, which is, the irony is so thick because Bell was the strongest advocate of that theory. And people are going around saying he proved it. It's impossible. I mean, this is just, the history here is so upside down and backward. So you might hear that and say somehow it just doesn't make the right, it can't make the same predictions as standard quantum mechanics. That's just not true. The other thing I heard when I was, again, I wasn't given the theory, but I was just told by oh, it's ad hoc. It's very artificial. It's kind of all, held together by Scotch tape, and it's ugly. And all you can say is those people just never could never have looked at the theory, because the entire theory is non-relativistic theory is written down in two equations, neither of which is ugly. They're both quite beautiful. They're both very simple. One of which is Schrodinger's equation, which everybody uses. And the other of which is this guidance equation, which tells you how the particles move. And it's also a very, very simple, almost inevitable equation to write down. So you first have to convince yourself there's nothing wrong with theory. Then you ask this question, but why don't they pay attention to it? Now, there's a nice book by Jim Cushing called, what's it called? Copenhagen Interpretation, and no, Historical Contingency and the Copenhagen Hegemony, I think it's called, by James Cushing. Cushing was a physicist. He got interested in this question. And the whole point of his book is that there is no good reason why people don't pay attention to the theory. I mean, his thesis, he calls it the Copenhagen hegemony, is that it's purely sociological. And the sociological move that's often made, and you'll hear many physicists make it today, is to say, oh, but if that makes the same predictions as standard quantum mechanics, why should I take it seriously? The immediate thing you notice as a logician is, but wait, making the same predictions is a symmetric relation, right? If A makes the same predictions as B, you can't claim that as a reason to ignore A or a
Almost
reason
a
to ignore
statement that it
B,
just happened
right? I mean,
historically and it's completely
yeah.
contingent.
And this was Cushing's thesis. Cushing's thesis was, if the pilot wave picture had gained adherence early on, which it could have, because Du Bois comes up with it in 1920, I now know 1923. It's even earlier than I read, 1926, certainly. So the theory's around from the beginning. If it had adherence and they were as forceful and clever as Bohr in fighting for it, and had sidelined Bohr and sidelined Copenhagen, then they'd be saying, later on, if someone comes up with Copenhagen, they'd say, but you make the same predictions as our theory. Why should we pay any attention to you, right? I mean, this is the logic of it is manifestly not rational about the things physicists will say. Now, physicists who have learned something about the theory, which is a small minority, and don't like it, and there are people, David Deutsche doesn't like it. David Wallace, many worlds people don't like it, but some of them at least know what the theory is. Nowadays, they'll say things, oh yeah, it works fine for non-relativistic quantum mechanics, but not for relativistic quantum field theory or something like that, right? I mean, the first thing to notice is, of course, that can't have been the objection back in 1926, because there was no such thing as relativistic quantum field theory then, right? And then you have to go into details, into very technical details about quantum field theory and the status of standard quantum field theory and the ways you might use this approach to do quantum field theory. It gets to be a complicated discussion, which only a handful of people are capable of even having, because most physicists don't know about the theory, don't care about the theory. They've been told to ignore the theory, and they do. They don't know about it. I think an average physicist would not have any good objection and wouldn't even be in a position to make one, because they don't even know what the theory is.
Hmm. Is there not an argument to be made that on the one hand, the pilot wave view actually has to assume more? If it has the same predictive capacity as, let's say, standard quantum mechanics, but then is
Mhm.
also assuming additional stuff by way of physical things that exist in the world. That's stating more than is necessary to achieve the same, level of predictive power, for example. And so I guess some people would say, any theory that seems that has more in it than is necessary to achieve the, let's say, the predictions,
Mhm.
is likely not to be the right one. Sometimes it would be called like Occam's razor, or
Yeah,
various
yeah, yeah.
versions of this. I think David Deutsche even has a version of this in his like hard to very good explanations. Um, what do you make of that challenge towards this theory?
Well, the first thing to say is you have to be clear what you're comparing it to.
Hmm.
So if you compare it to standard quantum mechanics, which is not many worlds, right? I mean, again, there's another piece of rhetoric that's sometimes put out that they say, oh, Everett just is quantum mechanics. No, that's not true. It isn't quantum mechanics, standard quantum mechanics. Standard quantum mechanics, as you were taught it, and as I was taught it, and as von Neumann wrote it down in his book, Mathematical Foundations of Quantum Mechanics, is a collapse theory.
Hmm.
And in a collapse theory, for it to be a good physical theory, you actually need a good physical theory account of the collapses. And that the standard theory does not have. It just says stuff like, oh, when you make a position measurement, then the wave function collapses to one or another position eigenstate. The thing I just said is it false anyway, but okay, let's leave that aside. But the point is, measurement appears centrally in the statement of the theory. When you make a measurement, then X happens. When you make a position measurement, then X happens. When you make a momentum measurement, then X happens. And again, Bell has a beautiful paper called Against, quote, Measurement, not against measuring things, but against the word measurement. And you just can't say it better than he said. He said, the term measurement is just not the right kind of term that ought to appear in the statement, in the foundational statement of a serious physical theory, because it's a vague term. You know, what does it mean to measure something? What interactions count as measurements? What we want is a theory, and Bell said, don't use the word measurement, use the word experiment. Sure, physicists do experiments. And when you do experiments, often one system interacts with another. But what does it mean to say that interaction is a measurement? Okay. I mean, what makes one interaction into a measurement and another interaction not into a measurement, right? Nobody has an answer to that that's clear and sharp. Measurement should not appear in the statement of the theory because it's vague. And this was the same kind of thing that people then, at a certain point, associated measurement with observation and observation with consciousness. And then you get to Wigner, Eugene Wigner, saying, oh, amazing, the mind-body problem, or, you know, minds are now central to physics. And Einstein just tore his hair out over this. He says, what do you mean? Can a mouse do it? Right? I mean, this is the kind of thing that Einstein immediately objected. He said, wait, to make a measurement, you have to have an observation. To have an observation, you have to be conscious. Is a mouse conscious enough to make collapse the wave function? Is a dog, David Albert, I spoke with him recently. There's a nice interview with the two of us and Robinson Earnhardt. And David said he literally heard Wigner say out loud, a physicist, great physicist, I think dogs can collapse wave functions, but mice can't. And you're going like, what are you talking about? Right? I mean, and that can't be how physics works. It just can't be. So the first thing you notice about the pilot wave theory is that you can state the theory without mentioning measurement. So to that extent, it is a much, much, much better, and I wouldn't even say in terms of simpler, but just from a logical point of view, from a conceptual point of view, it's a candidate for a foundational physical theory. And the standard approach, the one you learned, isn't. Because to state the theory, they're using terms that should not appear in any physical theory. So this thing about simplicity, that doesn't cut that way. Certainly you can't say properly the standard theory is simple. And this is also, Bell said he wants his physics in the equations and not in the surrounding talk, which all the stuff about collapses, measurements, and observations is not in the equations of the standard approach. Now, Deutsch is going to say, oh, but I don't need to talk about measurement either because I don't have collapses, right? You needed to bring in measurements to have collapses. And then you have to have a different discussion about how the many worlds works and how difficult it is to understand and how complicated. But I'll make one more, standard rants. I'll make one more rant here. This idea that I'm going to appeal to Occam's razor is often raised in exactly the way you raised it. You say, oh, here I have a theory that has postulates strictly less than some other theory. And so by Occam's razor, I ought to prefer the one with less. Well, here's an example from standard classical physics. Had electromagnetic theory, and Maxwell postulates there are electromagnetic fields and that there's charged matter, like electrons and things like that. And the whole point of the theory is to give you a dynamics for the fields and then also to explain how the fields couple to the matter. That's how you explain, radio antennas. Okay. So I move the electrons around up and down the antenna, which I can do directly. And then because of this coupling, that creates these electromagnetic waves. The electromagnetic waves go out, they get to your radio, that moves the electrons in your radio antenna, that creates a current that gets hooked up to a speaker, bang, radio. Okay. That theory has both charged matter and electromagnetic waves. Now, you could say, that's two things. Why don't I get rid of one of them? People sort of tried to do it, and they tried to do it both ways. One way was to say, I'm just going to have the electromagnetic field, and I'm going to get rid of the matter. The matter is going to be a singularity in the field. The matter is going to be just the field knotted up in a certain way, right? So that was pursued by Einstein and others for a long time. Or you say, I'm going to keep the matter and get rid of the electromagnetic waves. That was the Wheeler-Feynman approach to classical electromagnetism, was an attempt to do it all with the matter and say there is no electromagnetic field. Now, I don't think anybody should say, well, whatever this Feynman-Wheeler theory is, it's obviously preferable to the standard theory because it has literally less in it. I mean, they tried to do it and they kind of got something that's really weird and really hard to understand, and some equations that are very, very hard to solve or even know if they have solutions, and that involve backward causation. I mean, they had to jump through hoop after hoop after hoop to try and get this thing to work. Yes, it has less in it. But Occam's razor never says, if it's never proper to understand it to say, given two theories, just count noses and ask, which theory has less in it? Oh, the one that has less, that's a better theory. That's silly. There are just a dozen different directions in which one evaluates how plausible a theory is. How complicated are the equations? Right? I mean, there are just lots of things to say. How hard is it to make a connection between the theory and experience and observations and so on? I mean, there are all these different dimensions, and to bring in Occam as if Occam's going to settle this issue in 2 seconds is just a philosophical error, right? It's a methodological error. If it were like that, all physicists would have jumped on the Wheeler-Feynman theory as soon as it existed and said, "Oh, good, we can get rid of the electromagnetic field. We're all gonna go with Wheeler-Feynman." They didn't, and they were perfectly right not to. You had to give up a lot to get that theory.
Yeah, I certainly agree with that, and also just how much is in a theory versus is not in a theory is not always very well defined in any case. One thing that does come to mind though there is when we are making a selection of what is the right physical theory, we are optimizing across a number of different things. One obvious one is just the predictive power or the explanatory power of a theory. That's a yeah, that's a sort of a non-negotiable. But then there's a sort of like intuitive resonance with us. To what extent does this description make intuitive sense to us? And that one I often worry about because our minds are not necessarily evolved to understand deep physical laws, and sometimes I wonder if we're over optimizing for a physically or an intuitive grasp of what a theory says. And in particular, in the case of the last 40, 50 years of argumentation around how to understand quantum mechanics, I do wonder if this is an example of a case where there is never going to be a satisfactory optimal point on that sort of intuition axis. Do you ever think about that sort of question or that approach? To what extent is the human mind capable of intuiting this theory?
Well, you look into intuition is intuition is an interesting word. Um, and this idea that we find quantum mechanics hard to understand because we are programmed to understand things in certain terms,
Mhm.
and the world just isn't explicable in those terms. That was Bohr. That was a big part of Bohr's approach, right? And there's a long story here. Bohr grew up in a place where neo-Kantianism was very uh, rife, and Kant had this idea that um, we impose structure on the world. We impose, as it were, our conceptual structure on the world, right? I mean, Kant said this about space and time. Space and time are just the forms of our intuition, right? Space and time live in our heads. They're not actually part of the physical world. Now, that's very hard to do physics without space and time, okay? And Bohr sort of said, oh, well, if we get to a point where we can't do this imposition of these concepts, then you should just give up on wanting an intuitive understanding and so on. I think there are two aspects to this. Let's very clearly separate.
Mhm.
Should we expect the microphysics or the ultimate foundational physics to be intuitive? No. Why should we? In a certain sense of intuitive, that is intuitive in the sense that, oh, I can make sense of this in the same terms as I understand everyday life. Um, I mean, for Kant, it meant you had to do it with Newtonian physics. I mean, Kant actually thought that physics had to be Newtonian in certain respects, because again, kind of that's intuitive, you might say. No, of course not. And none of these theories are intuitive, right? The pilot wave theory certainly isn't intuitive. It presents a picture of physics that's profoundly non-Newtonian and profoundly non-local and profoundly not what you were expecting, right? It's not as far from what you were thinking. And when you learn relativity, you start out with an intuitive picture of space and time, and you learn relativity, and you say, oh, maybe that's not right at all. Maybe foundationally, space and time have an entirely different structure than Newton supposed and argued for. Of course, you should expect that as a physicist with no reason to think. However, 2 points. One is there is one thing where there's intuition, which is just what philosophers call the manifest image of the world. This is not microphysics. It's how does the world present itself to you when you just open your eyes, right? Okay, there's a table in front of me. There are 4 chairs. There's a cat. The cat's alive, stuff like that. You have to start from that to do physics, because what else are you going to do? I mean, you have to start thinking you know something about how the world behaves to do physics at all. And you start with, oh, I notice when I let go of this, apple, it falls to the ground. That's in a certain sense intuitive. We don't reason our way to that. That's just something that's presented to us. Again, that's what Sellers calls the manifest image of the world. That you have to have. If you don't make connection in your physics to that, then your physics doesn't make connection to the lived world, to the world of the experimenter, to the world of the observer at all. And then you don't know what the physics is about. It's just some fantasy. I mean, somebody says, okay, here's a physics with a 10-dimensional space-time and anti de Sitter space-time and blah, blah, blah. And you say, okay, but that has nothing to do with with my world. You may have described some mathematical object, but I can't connect that to anything in my world. Here's a theory where space and time have only 2 dimensions, right? Okay, that's a kind of interesting toy mathematics. That's not even proposed as a physics. Why? Because I can't connect it to the lived world. Then there's the second question you asked, which comes up a lot, and I think Weinberg used to push this. A lot of people push this. They said, well, maybe we're just not smart enough to understand fundamental physics. Maybe because our brains evolved to deal with the world only at macroscopic scale, at the scale of, hunting an antelope or whatever, or foraging, right? That's what we had to be good at to survive. And it turns out a kind of quasi-Newtonian picture is pretty good at that stuff. Maybe our brains, our intelligence is just not well suited to understand microphysics, or equivalently cosmology, right? Physics at large scales that have nothing to do with everyday life. And my reaction to that is say, well, that's an interesting possibility to bear in mind. However, we've done awfully well at coming up with theories that are really, 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 really good. I mean, the best prediction
Mhm.
in the history of the universe is the anomalous magnetic moment of the electron. That's not everyday life. We've managed to come up with a theory that gets that right to 14 decimal places. And we've managed to come up with theories that kind of explain the distribution of galaxies and structure formation at cosmological scale. So, sure, maybe we're not smart enough, but we have no evidence. All the evidence is to the opposite. All the evidence is that we've developed a kind of generalized intelligence that is up to problems that are very, very, very far from the evolutionary problems we had to solve to survive. That we just know we can because we do it all the time. So, I can't dismiss that as a worry, but how are you going to find out? The only thing you can do is keep pushing, right? If you want to know how far you
Mhm.
can go with the intellectual capacities you have, the only way to find out is keep pushing and see if you finally really hit a brick wall. We haven't hit a brick wall yet,
Mhm.
not with respect to physics. What we've run into is this kind of morass of confusion that grew up around quantum mechanics that's, makes people say all kinds of strange things.
Yeah.
Um, but it's not like, gee, here's a phenomenon, physical phenomenon that we've been incapable of. The Higgs, the Higgs mechanism. I mean, all the stuff. And you go and you build these big accelerators and you find the thing. I mean, it's amazing, right? You set up gravitational wave detectors and you find them just as they were predicted. So we're still doing real well.
Yeah, I think on that final view, that is definitely something that you are in agreement with David Deutsche on, because he's got this view of anything, basically any problem is solvable. Is solvable is his view. It does raise the question of, at least maybe a more practical question of the approach to solving these problems. Um, no doubt our human minds have evolved for different purposes, and it turns out they've been very good at very many things. Um, but I do sometimes think, trying to tackle a big problem like understanding quantum mechanics is kind of like, I don't know, taking a toothpick to a demolition site and knocking down a building with a toothpick. And one could do that for 40 years, for 50 years, and potentially eventually the structure will fall down. But potentially a better or more practical approach is actually to build a wrecking ball. And so one question that comes to mind is, in advancing physics, whether it's physics itself, philosophy of physics, um, is there enough emphasis put onto, let's say, building the machine to do that, whether that's building computational resources to understand fundamental physics, to explore foundations of physics. I don't know if this is a topic that you look into very much at all, but what are your
Well,
what are your views here?
I mean, let's just pause for a second and look at what's happened over the last 50 years in physics. So, what's
Hmm.
commonly said and is correct is that the standard model was completed, you know, by the early 1960s. You got Higgs and other people putting the Higgs particle and the Higgs field in as kind of last piece
Hmm.
of the standard model. That led to all kinds of interesting predictions that you had to build big machines to test, and and they finally did, and they put the money in, and they found the things, and this is great, great success. What was left after the standard model was gravity, because it doesn't account for gravity, and gravity, as treated by general relativity, has a very different character than the other forces, than electromagnetism and the weak and strong nuclear forces. And so and the mathematical structures you use to do general relativity and to do quantum theory are just different, and they don't kind of mesh together in a natural way. Um, So I would say, since then, the experimentalists had lots to do. But then there's this lingering question. We know we don't yet have a final theory. Well, how do we come up with one? Well, for 50 years, the high energy physicists pretty much put most of their marbles in string theory, um, which is a very strange thing to do because of the history of how the theory was developed, which was kind of happenstance.
Mhm.
I mean, the mathematics was developed to try and solve a problem, which it was later understood that's not the solution. And then the mathematics kind of took on a life of its own, and it was just developed for fun by mathematicians. And then there was this proposal, oh, maybe we can use string theory to unify everything and to give an account of gravity. And then there was the idea that string theory was so constrained there would only be one of it. And then they discovered, no, there are 100 billion different theories. And I mean, all of that at the present moment looks like an awful waste of resources. I mean, I'm not saying people shouldn't have pursued string theory, but the number of physicists, amount of effort,
Mhm.
theoretical effort, mathematical effort, and intellectual effort that went into that one approach, which never had a thread of empirical support. Uh, okay, not such a good idea. Um, what should we be doing? I mean, when you say build a wrecking ball, of course, if you knew how to build a wrecking ball, if you knew you were knocking down a building with a toothpick, and furthermore, someone came along with the plans for a wrecking ball, it wouldn't take
Mhm.
long to study that and say, we'd be, it would be good to divert some of our toothpick funding over to wrecking ball construction funding. Because at the end of the day, we'll be more efficient at this business. Um, sure. The question is how do you make progress at this? The main problem, as everybody knows, is that though, first of all, the low hanging fruit has all been picked,
Mhm.
especially in terms of empirical phenomena, right? We've sort of finished everything that is obvious to see. And so we're looking for subtle experimental clues, observational clues. And on the theoretical side, I think we would be doing much better to spread the resources around and have
Mhm.
people pursuing many different approaches. Um, and to start, as I would say, philosophically, trying at least to get a clear statement of what the problems are and what would
Yeah.
constitute solutions. I don't think that's done. I think often it's just, oh, here's some math. Let's do some more math. Let's make up some new math. Let's write, ER equals EPR papers that, I mean, these things are not well thought out. They're not well argued. And because physicists have not been trained to do that, they've been really well trained to solve equations and to build certain kinds of mathematical models. But this is not a matter of doing that. And I think they're not well trained to do it. And there tends to be a lot of bandwagoning and, I don't think it's been very efficient.
Yeah, that definitely resonates. Not just within science, but just technology more generally. These things done without an underlying philosophy becomes very undirected, and you're solving hard problems, but why? And and then why build in the direction you're building in? I guess this connects very nicely with what you're doing at the John Bell Institute. I take it that's sort of like a big focus. Why don't you, to bring us towards a close? Why don't you share a little bit about the institute, your plans for it?
Yeah. So, I mean, this is a perfect segue into it because, look, my undergraduate degree is a joint degree in physics and philosophy. My PhD is actually in history and philosophy of science. I don't have a philosophy degree in a philosophy department. Um, when I went to Rutgers, I fell in with Shelley Goldstein, who's a mathematical physicist in the math department, who's an expert in the pilot wave theory, which is how I learned about it, and became friends with David Albert, who got his degree in theoretical physics, but ended up in a philosophy department at Columbia because he was interested in foundational issues, and he couldn't pursue them in a physics department. His first appointment was in a physics department, but he couldn't do it. And so, in New York, in that area, we had a very nice group of people drawn from philosophy departments, math departments, physics departments who were talking to each other. And we all recognized that everybody brought a different set of tools to the discussion, and all the tools were necessary to make progress.
Mhm.
You can't just have a training in philosophy, but not physics and math and do this. But in a way, you can't just have a training in math and physics and at least no philosophical, you know, well-developed understanding of philosophical method and so on, and do it either. And so the way you make progress is to get people from these different backgrounds together in a place where they can talk to each other. And not only that, but the talking has to be done differently than is done in a standard setting. So in a standard conference, somebody gives, I don't know, a 30-minute talk and there's 10 minutes of discussion, and then somebody else gives a 30-minute. And when you're dealing with, there are topics where maybe that'll work. These topics are not like that.
Mhm.
The considerations are too complex, and the people are coming with their backgrounds are too different. You often have to do a lot of filling in and explaining what you're talking about to somebody who's coming from a different place. You need a lot more time. You need a lot more freedom. You need a lot less constraint of a schedule. And I ran for many years a kind of a workshop up in Lake Placid with a few of us, and we came year after year and did this. But I think this is just the way you make progress. And so what I'm trying to do is create this Don Bell Institute devoted to being a physical place where these kinds of discussions will occur. Just 2 weeks ago, I mean, I'm here now since people might wonder, I'm just going to take the opportunity to show you what we're talking
Oh,
about.
lovely.
Is
Yeah,
I
do
walk
it.
out right
Do it.
here, and this is where we are.
This is a
So
far cry from my cold office in Cambridge.
yes, it is. It's like the most beautiful place in the world, in Croatia on the island of Hvar, a tiny little village. But we have the opportunity, if we can. I mean, I came here. I was looking for a place to do this. I found this place. We built a lecture room. We built a breakfast room. We can put on workshop. We can put on summer schools. But I don't own. What I'm trying to do now is get enough money to actually purchase the location and then
Mhm.
continue to build. We would
Mhm.
have have the possibility here of putting another building up. You could, in my imagination, I could explain everything that I would hope in 10 years might exist here. But even now, it's up and running. We had a workshop two weeks ago on positronium, which, this is not a topic that's talked about much. Positronium is a bound state of an electron and a proton, and a positron, and the electron and positron eventually annihilate, and then it will decay into either two or three photons and so on. Very interesting physical and conceptual questions about that. And we had physicists, we had experimentalists, we had philosophers, we had some people with philosophical backgrounds. And again, it was very loosely organized, relatively few talks that went on for hours and hours because everybody was always interrupting and saying, can you explain that? Can you explain that? And I think it was just productive. It was just much more productive than the way things are done standardly in academia, which just don't manage to get across much, especially to an audience that's not already part of a very select sub audience. So yeah, what I'm trying to do, I mean, the John Bell Institute exists as a group of people.
Mhm.
We've got a faculty, we've got a bunch of fellows. You can just go to www.johnbellinstitute.org to see about it. I want it to exist permanently as a physical location where people can come and organize things in a relatively cheap way, quite honestly, in a really nice location, and one that is conducive to people just talking, uh,
Yeah.
and discussing each other.
It's a fantastic vision. Obviously, I will include all the links to the institute, the
Yeah,
website
there's the
in the show
GoFundMe.
notes.
So this is, it's taken, there have been all kinds of complications, and I found this place, and then COVID came and that messed everything up. And then there were some Anyway, we're finally at a point where we're really trying to see if we can purchase this place, and there's a GoFundMe campaign for it. And I must say, I've been on a few podcasts that the reaction has been very gratifying, because they're people who are not academics, right? But they're interested. And they say, yeah, this is good stuff. I mean, this stuff needs some support. And I mean, just so people know, it's almost impossible to get regular funding to buy buildings, right? That is, many of the funding institutions will not give you money for infrastructure. They'll give you money to hire postdocs or run conferences. What we need to do is get the infrastructure. So that's what we're trying to do now. And if we can purchase it, then there's a long-term plan to kind of develop this into a thing that will basically operate during the summers, and we'll have conferences in summer schools and workshops and things.
Yeah, fantastic. I definitely recommend people click on that GoFundMe, click on the website. On the website, actually, you'll find a page on book recommendations or book reviews. I think maybe that's a nice place to bring us to a close. Many good books there. You're extremely well read and widely read. If I had to ask you which book you have most gifted to somebody and why, what book would that be?
Well, it's funny. I did an interview once, and standardly at the end of the interview, the question is, give us 5 books, not by you, in your field that you would recommend to somebody interested in this field. And what I said, and I will say again, was, well, really my recommendation would be to buy John Bell's Speakable and Unspeakable in Quantum Mechanics and read it 5 times. I mean, it's not a single book. It's a collection of essays, and the essays are at all different levels. So there's some like Quantum Mechanics for Cosmologists, or 6 Possible Worlds of Quantum Mechanics, which are written for non-specialists, certainly non-specialists in this, to explain the situation. Then there are these kind of intermediate level things that have more math in them, but he's a very gifted writer and a very clear thinker. And then they go up to, very technical papers that really only a trained physicist probably would be interested in. But man, you can learn a lot from Bell, and on every topic you can learn a lot. He has a paper on how to teach relativity, which is just kind of a gem. He has a paper on the pilot wave theory. He has a paper on the collapse theories called "Are There Quantum Jumps?" The paper that I mentioned against measurement is an absolute classic. La Nouvelle Cuisine, which is a presentation of his own work, and Bell's theorem. All of these are just, you can never go wrong reading and rereading Bell, because his only flaw as a writer is that he's too concise. He expects too much reader. You'll like say the right thing and say it clearly and just say it once. And if you're a lazy reader, it's easy to read over it and not appreciate what he said. And then I mean, I'm the opposite. I just take a 2x4 and bang people over the head 100 times in a row, because my experience is they don't pay enough attention. So he's an extremely elegant, funny, precise writer. And all I can say is, if you're going to read one thing, get that book and just sample. I mean, you can sample the different chapters and find ones you like and just really study them.
Yeah, fantastic. Great recommendation. I might also take the chance to drop in that you've written several very good books. I've just finished I think it is your most recent one on the philosophy of quantum mechanics. Really enjoyed that, so we'll link that as well, and would recommend that. Tim, it has been an absolute pleasure speaking with you today. Thank you so much for making the time.
Thanks for having me. It's been fun.
Thanks for listening to this episode of the Paradigm Podcast. If you're enjoying this podcast, please consider sharing it with friends and family and leaving a 5-star review on your favorite podcast player. This goes a long way towards boosting our visibility and helping us attract even more fantastic guests. You can also head on over to our website, where you'll be able to submit questions for our guests, get access to special Ask Me Anything episodes, and some other nice perks. The Paradigm Podcast is free, but donations are very much welcome. For more, check out the links in the show notes. Thanks for listening, and I hope you'll join me again next time.